The whole universe is weird. What can I tell you? Okay, so let's take a look at the stuff that we talked about last time, and then we'll continue. And I was going to show you guys a picture of the sun. So we see the sun, we said, has a core, and this core is where all the fusion happens, where all the protons we call hydrogen atoms, the protons, they collide. When they collide at high speed, they overcome their mutual repulsion, they fuse together. Eventually, four protons basically become a helium atom. And since the helium atom has slightly less energy than four hydrogen atoms, that difference in energy becomes the difference in mass becomes energy via, E is equal to mc squared. It becomes pure energy. And then this energy has to reach the surface of the sun. So that's going to take a while. The photons here move around. They go up, they go left, they go down because they don't have any eyes. They don't know which direction they're going. They don't have, Google, what do they call Google address, Google map. There's no Google Maps for them. So they got to move blindfolded all the way to the surface of the sun. So in this area, what we call a radiative zone, this is where all light is moving the energy out. And we said there's three ways to move energy, right? So to transfer energy or energy transfer takes either radiation, light, convection, which is, hot stuff going to the colder area, right? We just said the second law of thermodynamics. Space is cold. Here, bubbles of gas are hot, so they're moving outward, and they're moving via these little convection cells that eventually become as big as the moon. Some of them become as big as the earth. They're big, gigantic bubbles. These bubbles move up. As they move up, they become bigger and bigger. We call this the convection zone. Now, these bubbles, as they move, since they are protons, right? They're just protons and electrons. So it's electrical. They're electrical. Even though they're positively charged, they're still electrical. So when this electricity moves, it makes magnetic field. So the magnetic field is generated by the movement of the protons, basically, by the movement of the electrons. That's what's generating it. So these interaction between the magnetic fields and the convection cells, that's what we see here. We see at the surface of the sun. And so when we look at the sun, we see sunspots there. We say the sunspots are the base of those magnetic lines of force. When they pierce the sun and they come right on out, and then they go right back in. So when one of them comes out and goes back in, gases that explode from the bubbles, they follow this magnetic lines and they trace it so we can see the actual magnetic fields. They're traced out by these gases. We call these prominences. And so we said if the prominences are at the edge of the sun like this, we call them a prominence. But as the sun rotates and they come into view against the background of the sun, because the prominences are a little cooler, the sun itself is hotter. We see them as these dark things, these dark lines we call filaments. So these filaments are exactly the same thing as the prominences. Then we said these bubbles, by the way, we also call them granulas or granulas, whatever you want to call them. The whole effect is called granulation. So the surface of the sun is covered with these granulas. All right, now the sun has three layers of atmosphere. These three layers of atmosphere are called photosphere. Photosphere is what we see. When we look at the granulas, we're looking at the photosphere. The bottom of the photosphere is what we call the surface of the sun, and it's moving, continuously moving. It's not like the Earth's surface. It's a ball of gas, right? So a ball of gas is continuously moving, doesn't have a real surface. And then the bottom of this photosphere, photo means light, sphere means sphere. So it's a sphere of light. Every time you look at the sun, you see photosphere. Then at the bottom is about 6,000 degrees. At the top of the photosphere is about 10,000 degrees. Now remember, the Earth's atmosphere gets colder and colder as you go up higher and higher. Like at 20,000 feet, you freeze to death. But here it's getting hotter and hotter. It's the opposite of the Earth's atmosphere. Well, the bottom of the next layer, which is called a chromosphere. Chromo means color, sphere, sphere. So the color light sphere. So we have photosphere, and top of the photosphere is the bottom of the chromosphere, which is about 10,000 degrees. The top of the chromosphere gets to be about 100,000 degrees. And then there is corona. Corona is the crown of the sun on the outer. And it's millions of miles in diameter. So you're looking at the photosphere, the light sphere of the sun. Here we can see those beautiful prominences here, more prominences here, more prominences here. And these same prominences, as the sun turns in, they become these filaments, these curly filaments. So in these filaments, you can tell where the base of the magnetic lines are. So the magnetic lines, one base is here. Maybe this is the north or the south, I'm not sure. And this one here on the other side will be south. So south, north, north, south. I don't know which way is which. South, north, like that. So these are all the filaments. Filaments are coming at you right here. This guy is coming directly at you. But because it's cooler than the sun itself, than the photosphere, it appears to be dark. All right, so that's the photosphere. And then, I'll show you this later. And then what generates the magnetic fields is the movement, we said, of the atoms. Because the atoms are charged, moving charge creates electric field. As it moves, it creates a magnetic field. So now if you have a compass at home, take your compass, put it directly next to a wire, any kind of wire in your house, either the wires in your wall, the wires outside your wall, put it there, and the compass goes crazy. There's a magnetic field around your wire. So try it. If you have a compass, please try it at home. It's not dangerous. All right, so this is the magnetic field of the Earth. I know, it looks pretty impressive. So this is a north magnetic pole. This is a south magnetic pole. If something ever gets stuck here, like an electron, it travels from the north to the south. That's the direction of the magnetic line of force, we say. All right, so this is crazy. In San Diego, the true north, like the axis of the Earth, is the true north of the Earth. And then we have a magnetic north. The magnetic north and the true north differ by about 13.5 degrees in San Diego. If you go to Denver, Colorado, that's only 12 degrees. So as you can see, the magnetic lines are really crazy on the Earth. It looks like a big ball of twine that has been played with a kitty cat. That's what it looks like to me. All right, now, do all stars move energy the same way? No, they don't. So now this big M from now on, this big M represents the mass of the sun. So when we say, like, how big is that star? We're talking about how massive it is. So mass of the stars is what's important. So this stars that have less than half the mass of the sun. So the sun is about 333,000 times the mass of the Earth. So if something is about 150,000 times the mass of the Earth, that'd be a really tiny star. And that tiny star has energy again here in the center. That energy is transferred to the outside only via those convection cells, only via bubbles. As the star gets more massive, between 1/2 and 1.5 times the mass of the sun, energy in the center is moving via radiation, light, and then the bubbles. Here in the massive stars, it's a different story. In the center, we have convection, which is really strange, right? These are supermassive. They can be as massive as 100 times the mass of the sun. Gigantic stars, supermassive. These supermassive stars are interesting because what's important to the star is keeping itself alive. What's important to a human is keeping itself alive. That's why we go to the doctors, right? So we can keep alive. So the star also tries to keep itself alive. So what's killing this star? What's killing it is mass, it's gravity. It's deadly scared of gravity because it's a ball of gas, right? This ball of gas will be crushed if it didn't make energy. In fact, it does get crushed when it doesn't make energy. That's where supernovas come from. So here, it has to make enormous amounts of energy because it's got lots and lots of mass, so lots and lots of gravity. So it's got to make huge amounts of energy. So how does it make huge amounts of energy? By bringing in fresh fuel to the core. So the fresh fuel is brought to the core by these bubbles. Fresh fuel comes in, it gets used up, and it goes back out. And then fresh hydrogen comes in, gets used up, and goes back out. So this really helps the core of a massive star. And then on the outside is where radiation takes it the rest of the way. So massive stars are the opposite of the sun. Now the sun, continuously these bubbles explode, and there's magnetic fields, and a whole bunch of hoopla going around the sun. What that does, because the electrons and protons and helium nuclei, they're all over the place exploding, these get released into space in the form of solar wind. That's what solar wind is. It's a wind caused by, it's a motion of these we call solar wind. It's not really a wind. It's just a motion of these particles coming from the sun. So as they travel towards the Earth tries to protect itself. Well, it protects us, life. And so the magnetic fields of the Earth, as it travels through space, this comes from the north and goes to the south. These are the magnetic lines of the force of the Earth. What causes the magnetic field of the Earth is the iron core. The iron core of the Earth has also lots and lots of electrons. Iron has a lot of electrons in the outer shells. So in effect, it's a flow of electrons. And when these electrons move, they cause a magnetic field to form. And that's the cause of the magnetic field of the Earth. But it's millions of times less strong than the magnetic field of the sun. As the solar wind is coming towards the Earth, it'd be deadly. We'd all be dead if it wasn't for the magnetic field of the Earth. So the Earth's magnetic field protects us. It's like a shield. So my cursor right here, let me see if I can get a fancy cursor. There's my fancy cursor. All right, so here's my fancy cursor. Here's an electron coming from the sun. As it comes from the sun, there's a shield. It's a magnetic field of the Earth. It goes shoo like that. It gets deflected. So electrons go this way, electrons go this way. They never actually come into the Earth. However, there's two areas where they can actually enter. One is in the north here, one is in the south. They can come in through the north and the south. And that's what's causing the auroras on the Earth. So auroras are caused when there's a lot of solar wind that come towards the Earth. The electrons and protons enter the Earth's atmosphere from the North Pole and the South Pole where there's holes. And they see atoms in the Earth's atmosphere. They recombine. So when you're watching recombination, make sure you understand that recombination means emission of a lot of energy. So when a free electron from the sun comes in here and joins an atom in the Earth's atmosphere, it has to give up light. That light we call aurora. So when auroras happen, you see this. And this is a beautiful thing. It's a beautiful aurora. This is from Alaska. And in Alaska, there's a lot of them because it's so far north. It's close to the North Magnetic Pole. In fact, the North Magnetic Pole is in Canada. It's not at the North Pole of the Earth. And so here they're coming in, they get recombined with the atoms in the Earth's atmosphere. And also, you can hear them. It sounds like you're walking on leaves, like that. And they also move as in a curtain of light because the magnetic fields are moving. As they move, the magnetic fields of the Earth make this light also move around. So they appear like curtains. So they're continuously moving. And this is from Finland. In Finland, they see it all the time because they don't even have, much daylight in the wintertime. They have almost perpetual night. So you see it every night. It's a beautiful thing. There's a lot of tourists that go to like Iceland and Greenland and Finland and Canada and Alaska just to see the auroras. In the north, we call them Aurora Borealis. Borealis means north. In the south, we call them Aurora Australis. Austria means south, so Australia, south.
When is the best time for going there and watch them?
The best time to see it will be winter. in the north, in the wintertime in the south. And when there's a lot of solar activity, when there's, sun is shooting out a lot of solar wind. There's something called solar weather, sun's weather, space weather, they call it. So there's a place where you can actually check it out. They tell you what the space weather is like. I've seen it from San Diego too. You can see the auroras from San Diego sometimes when there's a lot of particles come from the sun. But you got to go someplace dark, like on top of Mount Laguna, to see them. If it happens during class, I'll let you guys know. So what you're looking at is called, what layer of the atmosphere of the sun is this? We have photosphere, chromosphere, and corona. So which one is this?
The chromosphere.
This is the photosphere, right? Photosphere, the light sphere. What you see, every time you look at the sun, you see photo, light sphere. And then you see chromosphere. There is the chromosphere. If you see the chromosphere, you know you've seen it because it's colorful. It's like this. It's reddish like this. Beautiful. But unfortunately, you only see it during the eclipse of the sun, like this. You see this beautiful chromosphere around the sun. And then this is the corona. Now, the temperatures in the corona at the bottom are about 100,000 degrees. On top here, they're about 2 million degrees. Well, 1 to 2 million, they change. So now, I'm going to stick my finger into 2 million degrees. See what happens. So I just stuck my finger and nothing happened. Why didn't anything happen to my finger? It's 2 million degrees. It should be gone, right? It should be annihilated. What happened to my finger? How come nothing happened to my finger? So if you guys can figure that out, any guesses for a point? Because it's almost a perfect vacuum. There's hardly anything here, right? So even if something hits you, it's like 1 or 2 atoms, no big deal. 1 or 2 atoms are hitting you right now as we speak. Atoms are coming down on top of your head. It's something like, I don't know, every hour, at least 100 of them are hitting you, and nothing really happens. Well, some things do happen, but they have to happen at the right time, right? That's mutation. Like if at the time when a baby is being produced, right? When you have an egg and you have a egg producing embryo, at that point, if it's hit by one of these particles, it can make a difference because it can change your chromosomes. When that changes, you can come out with 2 heads. So it does change, right? Mutations happen because of these particles. So this is a good example of what temperature is. Temperature is not something you say, oh, it's hot, hot, hot. No, temperature is how fast these atoms are moving, right? So it's a measure of how fast these atoms are moving. This should be a good lesson for all of us. So temperature is a measure of how fast they're moving, right? Heat is energy. Heat is amount of energy. And there is these streamers. Sometimes there's so much activity here that you can see streamers coming out of the corona of the sun. Now you can see the north and the south magnetic field of the sun. Here's the north, here's the south magnetic field. You can see going like this. It's like a magnetic field of the earth, like that. It's a beauty. All right, this I already showed you last time. This is a Maunder period or Maunder minimum where there was no sunspots for a long time. So this is a number of sunspots from 0 to 200 sunspots a day. So Galileo was counting them like 20, 30, 40, 50 here, 80 here, And then this period, nothing between 1645 and 1725, nothing, hardly any sunspots. We call this the Maunder minimum. Bad things happened. Plants don't grow very well at all. And so potatoes are about the size of a quarter. Tiny little potatoes were growing. Not a good time on Earth back then. This is when we had the Black Death and everything else between 1645 and 1725, the Maunder period. All right, well, this is the sun. This is the spectrum of the sun. Now, how do you make a spectrum? Well, you can use a prism. The prism will spread this the light of the sun, so you can see individual components in the sun itself. And every one of these lines is telling you that there is an electron present from some atom. Every one of them is telling you the electron, this one here, belongs to calcium. The electron here belongs to calcium. Electron here belongs to calcium. Electron here that did the absorbing, it belongs to hydrogen. Let's see, this one here belongs to iron. This one here belongs to magnesium. This one here belongs to, I think it was manganese. So we know what's in the sun. We know what the sun is made of by looking at the spectrum of the sun. The absorption lines tell us the state of the electrons. In other words, is the electron on the second or the third level? Is the electron in an atom that is ionized or not ionized? Everything that you want to know about the sun is in front of your eyes. It's an incredible thing. All right. Any questions before I start the next topic? By the way, you know, I figured out that I'm giving you guys too long the lectures because the other class starts at 11:10 and ends at 12 something like that. So that's really weird, right? And so I'm giving you guys too long a lecture. So from now on, I'm going to make the lectures 10 minutes shorter or something. So we can't have two classes at two different times.
Oh, we love it.
Okay, great. Me too, man. My tongue is, you know, runs dry after a couple hours of lecturing. All right, so here's the heat transfer again. This is how energy, we said energy is heat, right? That's how it's transferred from the center of the sun to the edge. Excuse me. Now it's going to get interesting. Now we say two things. And you could take notes right now because I haven't written all this down. Of course, I'm going to make more videos for you about all this, but you can take notes right now. There's two things that I want to teach you right now. One is called luminosity and one is called brightness. What's the difference between luminosity and brightness? That's what we're going to do right now. So we say the star on the right side is very luminous. This is a luminous sphere. This is not as luminous. So what do you think luminosity is? Right? Luminosity. Luminosity is the energy output, right? Energy output per unit time in all directions. The reason I say in all directions because the stars that you're looking at, they have two sides, right? So there's a back side, there's a front side. So lots of energy is coming out of this guy here. And we say luminosity is the total energy output per unit time in all directions. That's luminosity. Basically, all the light that comes out per second, that's luminosity, right? In all directions. That's luminosity. So what's brightness then? Brightness. Which one of these looks brighter to you, the blue one or the orange one?
Blue one.
The blue one. All right, so what is brightness then? So brightness is energy output per unit area per second or per unit time. So now, if you look at a square centimeter, that's unit area, right? Square inch. So if you look at a square inch of this guy versus a square inch of this guy, there's more light coming out of the one on the left than the one on the right. That's interesting. So what is brightness then? Let me stop it real quick. Get my flashlight. Let's see, is this flashlight bright? I'd say it's bright. How do we know it's bright? Well, one easy way to see if it's bright is just stick it in your eye and go, oh my God, this is bright, right? So it's bright. All right, so, but is it luminous? See, is there a lot of energy coming out of this? Well, you know, you can't have a flashlight light up your whole house, can you now? Right? So if this thing was as big as a wall, then it'd be luminous. So it's not very luminous. So can you think of anything that is luminous in your daily life? I think Linda's trying to say something, but her microphone.
Would it be the sun?
The sun. Very good. That's right. The sun, right? Who said that?
Me, Lourdes. And then let me change my name.
Oh, sheesh. What's your last name? That's the most important thing.
Alcalá Guerrero.
Okay. You may want to write it down. Is it Guerrero?
Yeah, and I updated it so it shows now.
Okay. Yeah, but I don't see everybody at the same time, unfortunately. All right, Guerrero, thank you. That's right, the sun. Yeah, that's very luminous. So the sun is very luminous because every square inch of the sun, there's a lot of light coming out, like this flashlight, lots and lots of light. But it's huge. It's a gigantic surface. So it's very luminous, right? All right. So can you name something that is very bright but not very luminous?
The TV?
The TV. Does the TV hurt your eyes?
A little bit.
Really?
Moon?
You keep looking at it for hours and hours and it hurts your eyes, huh? Well, you
A
should
light
stop.
bulb?
Okay, very light bulb. Very good. Yeah. Yeah, TV doesn't hurt my eyes. You know, I can look at TV for like, oh my God, I just watched Dawson's Creek like 4 episodes in one night. And I'm still.
No way.
Yeah, I did. Yeah. So, yeah. So, okay. I would say the headlights of a car, they're very, very bright, but they're not very luminous, right? But they're very
A
bright.
laser pointer?
I'm sorry?
A laser pointer?
Laser pointer, very, very bright, but you can't, you know, you can have dinner with the light of a laser pointer, right? Okay, very good, thank you. So does everybody understand the difference between brightness and luminosity then? So luminosity is all the light, brightness is just a little bit of light coming out, but a lot of it. So that's,
So the moon is luminous or is bright?
I'm sorry, one more time?
The moon. How about the moon?
The moon is not luminous or bright. The moon is just reflecting sunlight, right? It's just a dark body. It only reflects 15% and it's just reflecting sunlight.
So it has to have its own energy, or
no. But if the moon was as, you know, as luminous as the sun, if it was reflecting so much like a big giant mirror, then it'd be luminous and bright. It's just that it doesn't reflect much. That's all. So the moon is not a good example of anything that is bright or very luminous. All right, so what makes something luminous is what we're talking about here. So what makes these stars that we're looking at, what makes them luminous? And luminosity is one of the fundamental things about the stars we're going to study. So what makes a star luminous? 2 things make a star luminous. One is the surface temperature. If the temperature is high, they'll be very, very bright. Have you guys ever seen like magnesium burn, like a little tiny piece of magnesium burn? I'm sure some of you have. This something we did in high school, right? Like potassium, magnesium. When you burn it, it's like the sun comes out. It's incredibly bright, right? Because it's burning at super high temperatures. So the surface brightness of the stars, the surface brightness, is caused by their surface temperature. The higher the temperature of the star, the brighter they get. So the sun is 6,000 degrees on the surface, and the sun looks like this. The sun is over here in the scheme of things. We'll talk about this in detail, don't worry. So what makes something more luminous than the sun will be more temperature. So surface temperature gives you brightness. Can you guys remember that? Write down someplace. The brightness of the stars are caused by their surface temperature. So something that is very bright and very big be extremely luminous. Like this guy here is very, very big and it's like 30,000 degrees on the surface. Sun is only 6,000 degrees on the surface. So let me back up here. So 2 things determine luminosity. Surface area, the bigger you are, the more luminous you are. So surface area and surface temperature. So surface temperature and surface area determine luminosity. So these 2 things are exactly the same surface, same size. The one on the light, The one on the left is higher temperature. It appears to be more luminous. So between the two of them, they're exactly the same size. The one on the left is more luminous because it's hotter. It's brighter. So surface temperature gives you more luminosity. Size also gives you more luminosity. These two are exactly the same temperature. This one is bigger, so it gives you more luminosity. So the stars that are bigger and hotter, they give you the most luminosity.
Could I ask a question on this?
Oh, of course. You always ask me. You can just interrupt me. I don't mind being
Okay.
interrupted by you, Linda.
All right, thank you. Okay, but brightness is defined as energy output per unit area.
Correct.
And on the luminosity, it doesn't say anything about area. It just
Correct.
talks
Correct.
about,
It doesn't. It does not. It just makes sense that if something is very bright and very big, you get more light. That's all.
okay.
Yeah.
All right, thank you.
Yeah. You're welcome. So now, introducing something called the Hertzsprung-Russell diagram. We're going to be playing with this diagram. It's the most important diagram in all of astronomy, right? And I'm going to go very slowly with this. I'm not going to hurry this up, all right? And so what it is the diagram of luminosity. This is luminosity. Up and down is luminosity. And we're using units as compared to the sun. So this is 1. This is how luminous the sun is. So remember how luminous the sun is? So that's 1. This would be 100 times more luminous than the sun. 10,000 times more luminous than the sun. 1,000,000 times more luminous than the sun. 1/100th as luminous as the sun. 1/10,000th as luminous as the sun. This is pretty much the range of what we call stars in the sky, in the universe. That's the range. We go between 1/10,000th as luminous as the sun and about 1,000,000 times more luminous as the sun. Left and right is called spectral class. Spectral class is surface temperature. So we classify stars based on surface temperature. The hottest stars are called the O stars, then the B stars, then the A stars, then the F stars, then the G stars, and the K stars, and the M stars. So how are you going to remember all this? Well, this is how we remember them. We say O, be a fine girl or guy and kiss me. Oh, be a fine girl and kiss me. That's how we remember this. Can you guys remember that? Oh, be a fine girl and kiss me. Be a fine gay guy or girl and kiss me. That's all you have to remember. And that's the surface temperature. They're based on surface temperature. So here we go, surface temperatures. Oh, it's about 40,000 degrees surface temperature. You don't have to remember it. Just remember it's pretty hot. About 40,000 degrees on the surface. And then B's are about, 20,000 degrees surface temperature, something like that. A's are about 10,000. F's are about 8,000. G's are, sun is a G, by the way. That's about 6,000. K's are about, 4,500. M's are about 3,000. So that's the range. Between 2,500 degrees surface temperature and about 100,000 degrees. That's it. That's all the stars that are in the universe. There's nothing beyond that. So why is that? Well, there's a reason for it. 2,500 degrees surface temperature are the coolest stars in the universe. You have to have fusion to be called a star, right? So if you have fusion in the core of the star, that's a star. If you don't have fusion, you're not a star. So the coolest stars have a surface temperature of 2,500. In the center, they're like 5 million degrees, but we can't see the center. So we have to classify according to the surface temperature. Now, What if you have a lot of mass and your center is like a, I don't know, 100 million degrees, a billion degrees. Your surface is going to be something like 100,000 degrees. Well, now you're making so much energy, you're going to blow yourself up. So on one end, you blow yourself up if you have too much. On the other end, you basically can't even start fusion. That's the range. And why is it called OBAs and all that? Because some Italian astronomer, a couple of hundred years ago, he classified stars according to the alphabet. So he had A, B, C, D, E, F, G. Turns out that some of those were not real, that they were repetitive. So this is what's left over from the entire alphabet. So that's why OBF, Fine Girl, and Kiss Me is remained now. Now, when we have this luminosity, in this case it's on the right-hand side, this luminosity versus surface temperature, all the stars in the sky, which we call regular normal stars, they line up beautifully here like this. And first people to notice this, guy named Hertzsprung and a guy named Russell. So we call this diagram the H and R diagram. I think they were both in New York at the time, in 1920s. So H and R diagram is the most famous of all the diagrams in astronomy. It's a diagram of luminosity versus the surface temperature of the stars. And we're going to be using this forever and ever and ever and ever. That's what it is. O stars, big bad blue stars. B stars, big, but not as big as the O's, big bad blues. A stars are white. F stars are kind of yellowish white. G stars, sun-type stars, are yellow. K stars, orangish. M stars are reddish. So next time you look at the stars, please remember, you're looking at different colors. Try to see the colors of the stars from now on, please. Okay.
I have a question, Professor.
Yes, please, yes.
Going back to the brightness chart of the luminosity, how come Sirius is so much brighter than the other stars if it's not relatively high on that chart? Like is it because it's closer?
This one, Sirius?
Yeah.
Very good. Who is this? This is
Vance.
Vance?
Yeah.
Vance, when I give you points, I got to give you your last name.
Oh, sorry, Vance Noel.
Thank you. All right, Vance, thank you for asking the question. This is Sirius. Sirius is an A-type star, right? It's an A star. And A stars are not that big. Remember, O stars and B stars are bigger, right? Much, much bigger, more luminous. It turns out that all the stars around the sun are these little tiny, tiny, tiny little red stars. It just happens that we have one star that is an A-type star. Let me see if you remember the A-type stars. This guy here is an A-type star. One of these is fairly close. It's about 8.6 light years from the Earth. So because it's so close, like you said, it appears to be very bright in the sky, so we can see it easy with the human eye. That's all. It's the brightest star in the sky, though. You'd be right.
Makes sense.
Yeah. Thank you for asking that. Good one. All right. So we're going to end the class now.